Welcome back to the sixth and final section of Chapter 6. In this section, we'll be looking at de Moivre's theorem and nth roots. And really, we're going to be looking at complex numbers today. But we've seen complex numbers before. We're going to be looking at them in kind of a vector sense and a polar coordinate sense, and we'll see how they're actually quite a bit easier to deal with in doing a lot of things. And we're also going to be finding nth roots of complex numbers, and we'll see some surprising stuff there. So I'm always kind of a little bit excited about this lesson because it's just kind of, there's a little bit of a blowing your mind towards the end of it. So our learning targets: plot points in the complex plane. We've done that before. Find the polar form of a complex number. That's new. Write the polar form of a complex number in the form of a plus bi. Find products and quotients of complex numbers using their polar forms. We've multiplied and divided complex numbers already this year. This is easier. And then find powers of complex numbers. We're also going to be finding roots, which are just fractional powers. So let's do a quick review. The complex plane looks like the rectangular plane, except instead of x and y, these are the real and these are the imaginary. And so we could have things like, say, u is 2 comma 4. So 2 comma 4 is a complex number. U would equal 2 plus 4i. Should have started with that one. V, let's have V equal 3 minus 2i. So we go over 3, down 2. So that's V, which is 3 minus 2i. We could add these together just for the fun of it. We've done this before. U plus V is going to be 5 plus then 4i minus 2i is going to be 2i. So u plus v is 5 plus 2i. So if we wanted to take a look at these as vectors, we have u, we have v. Hey, look at that. We make a parallelogram just like we do with vectors. So u, instead of just 2 comma 4, it's 2 comma 4 because we have the horizontal and the vertical components. V is 3 comma negative 2. The sum of the two is 5 comma 2. So again, the complex plane, the x-coordinate is the real value, the y-coordinate is the imaginary value, and coming from the origin, it's just a comma b for the vector. Remember the standard form, so z, a lot of times we write our complex number equals z. It's going to be a plus bi. And in vector form, that's just a comma b. The same as when we plot it, a comma b. We can find the absolute value. The absolute value is the same as the absolute value of the vector. It's a squared plus b squared, then we square root because it's the distance away from 0. So the absolute value of u is going to be the square root of 2 squared plus 4 squared. 2 squared is 4, 4 squared is 16, so we end up with the square root of 20, which is 4 times 5, so that would be 2 root 5. And so there's nothing new or different about that. There is a slight difference here, and that is it's the absolute value, which could also be called the modulus. What is complicated about that? If it says find the modulus of this complex number, you need to know that it means the absolute value. So it's purely a vocab thing, a definition thing. They mean the same thing. And it's the distance from the origin. It says in the complex plane, it's always the distance from the origin. So that is stuff that we already know, aside from this new word of modulus. So what about stuff that we don't know? The polar form of a complex number. We can write the complex numbers in polar form. Now, we didn't talk about this in polar form, but we did talk about it as vectors. Remember that vectors can be written as r and then sine theta, comma, cosine theta. That's polar form. R sine theta, r cosine theta. Doesn't that sound a lot like a polar coordinate? So that's just called polar form. It's not exactly the same, but being that it's a radius and an angle, it's called polar form. We've done this before. So if we remember the polar form, it's r cosine theta and then plus I sine theta. We have to have that I in there because it's imaginary. The A is r cosine theta, B is r sine theta, r squared equals a squared plus b squared, and tangent theta equals b over a. So it's the same thing as before. So if we had, say, u equaled, was it 2 plus 4i, I believe it was? We could write this in polar form. So r is the absolute value. We just found that. It's root 20, which was 2 root 5. It's the absolute value because the square root of a squared plus b squared is the absolute value. So r is the modulus, and then theta is called the argument. Tangent theta equals b over a. So tangent theta equals 4 over 2. So we would go to a calculator to figure out what is the inverse tangent. So let's make sure I'm in radians. We generally speaking, well, we could do this stuff in either radians or degrees, but I'm going to be in radians for this one. So the inverse tangent of 4 over 2 is about 1.107. So theta is about equal to 1.107 in our case. So we have the radius, we have theta. We could write u as 2 root 5 times cosine of 1.107 plus I sine 1.107. So that's how we can put it into polar form. If we had something in polar form, we wanted to get it back to rectangular form. Let's say z equals 3 times cosine of, say, pi over 3 plus I sine pi over 3. We're just going to multiply this through. Z equals 3 cosine pi over 3. Remember that cosine pi over 3 is just a number. Plus 3 sine pi over 3 times I. Sine pi over 3 is, again, just a number. Cosine of pi over 3 is going to be 1/2. So this is going to be 3 times 1/2, which is just 3/2, plus sine pi over 3 is root 3 over 2. So this will be 3 root 3 over 2 I. So we just multiply it out. If it's not one of the angles that we know, we'd use our calculator, we'd get a decimal, just like we did in that first example going the other direction. So putting them into polar form, taking them out of polar form, is something that you'll be doing, and it can be very useful. The out of polar form is nice because this is kind of how we recognize the complex numbers right now. However, polar form is going to make some stuff, such as multiplying and dividing complex numbers, much, much easier. So let's take a look at that. Multiplying and dividing. There's a great formula. So we have two complex numbers, z1 and z2, with r1 and theta1, r2 and theta2. When we multiply the two r's, and then we add the angles. When we divide the two r's, and then we subtract the angles. So let's have two, let's say z1 is going to be 3 times cosine of pi over 6 plus I sine pi over 6. And z2 is 4 cosine of pi over, no, I don't want pi over 6, let's go pi over 5. Why not? Plus I sine pi over 5. All right, so if we wanted to multiply them, z1 times z2, we're going to multiply the 3 times 4. And then it'll be cosine of pi over 6 plus pi over 5 plus I sine pi over 6 plus pi over 5. z1 times z2, 3 times 4 is just 12. Pi over 6 plus pi over 5, we have to have common denominator of 30. So we'll have 5 pi over 30, 6 pi over 30. So we'll get cosine of 11 pi over 30 plus I sine 11 pi over 30 multiplied. Whereas if we were going to multiply them the regular way, we have to distribute the I squareds, become a -1, and we have to combine those terms. It's not too bad. In fact, it's kind of 50-50 there. Like, it doesn't really matter which way you go. Division, however, is easier. So if we have z1 divided by z2, we'll have it's 3 over 4 times cosine, and we're going to subtract pi over 6 minus pi over 5 plus I sine pi over 6 minus pi over 5. So z1 over z2 is 3/4 times cosine pi over 6 is 5 pi over 30s minus 6 pi over 30s is cosine of negative pi over 30 plus I sine negative pi over 30. We could use some properties of cosine and sine. Remember, the cosine of a negative angle is just the same thing. So it's just cosine of pi over 30. And then sine of a negative angle is negative sine. So that would be minus I sine pi over 30. So both of these two last things are the same. Obviously, if we're using degrees, and it's just like, our angles are 12 degrees and 40 degrees, we'd have 52 degrees when we're multiplying. And if we were subtracting, let's say we're dividing the 41 divided by the 12 one, we would subtract and have 28 degrees. So with degrees, you don't need to find the common denominators and stuff. So that's even easier. So the Division is quicker doing it this way than doing the um, other way, because the other way was multiplication. You had to multiply by the complex conjugate on top and bottom, and then multiply both of them out, simplify. This is easier, but it gets even better when we're taking powers of complex numbers, because isn't z to the, not z3, z to the third, isn't that just z squared times z? So we'd multiply, and then we'd multiply it again. So the stuff in front would multiply and then multiply again. The stuff in the middle would add, then add again. And so if, let's say, our z is 2 cosine, we'll go 10 degrees, plus I sine 10 degrees. So z cubed would be z squared, which is 2 squared, so 4 times another 2. And then cosine, we had 2 times, like 10 plus 10 was 20, plus another 10, plus I sine 20 plus 10. Isn't this just 8 times cosine of 30 degrees plus I sine 30 degrees? Isn't that 2 cubed cosine of 3 times 10 plus I sine 3 times 10? Because we're adding 3 of them together, or we're multiplying 3 of them together, and it extends. So if we wanted to say go z to the 7th, this is just going to be 2 to the 7th times cosine of 7 times 10 is 70, plus I sine 70. I mean, 2 to the 7th is going to be a decent sized number that we'd have to figure out, but that's super quick. If we were doing this using the regular way, we'd have to multiply each of them out separately. We'd have to go z times z, the I squareds make -1, simplify, times z, I squareds make -1, simplify, times z, I squareds make -1, simplify, and it becomes really long. This, which is super quick and really just an extension of the multiplication, this is what de Moivre, that's what he proved and got to name this after him. Really, it's just an extension of the multiplication. I don't know. I'd be almost embarrassed to have it named after me. It's like, wow, I couldn't even come up with something original. I just had to extend something. No, he's famous. He's got his name on this and everything. So, I mean, I envy him. So, anyway, when you take it to a power, you take that r to a power, and then you just multiply the angle. This can be used backwards to find roots of complex numbers. So a root, an nth root, means that v to the n equals the number. So that means v would be the nth root of z. And an nth root of complex numbers, there will be exactly n unique roots. So if we have a fourth root, we're going to find 4 roots. They're all different. A third root, we're going to find 3 roots. They're all different. How do we do this? It gets kind of cumbersome, but it's the same thing over and over again. So z equals r cosine theta plus I sine theta. Then the n distinct complex numbers will have the nth root of r, and that is just the number. Like if you typed it into a calculator, that's what you'd get. Cosine of theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, where k starts with 0, and then you plug in 1, you plug in 2, you plug in 3, till you get to the number before the root. So when you include 0 in it, you have that n number of roots. So let's take a look at one. We have here's z, 5 cosine pi over 3 plus I sine pi over 3. So it's already in the polar form. If it wasn't, we'd have to put it in polar form. And let's take the third root. We want to find the cube roots of z. So we're going to find 3 of these. So we're going to plug this in. There's going to be the first one. It's going to be z equals the cube root of 5 times cosine of pi over 3 plus 2 pi times 0 over 3 plus I sine pi over 3 plus 2 pi times 0 over 3. We'll do our work here in a second. The second one will have the cube root of 5, then cosine of pi over 3 plus 2 pi times 1 over 3 plus I sine pi over 3 plus 2 pi 1 over 3. The third one though these aren't z's, these will be cube roots of z. Is going to be the cube root of 5 times cosine pi over 3 plus 2 pi times 2 over 3 plus I sine pi over 3 plus 2 pi times 2 over 3. And so we start out with 0. We have 1. We have 2. That makes 3 roots. And 2 is 1 less than 3, which is the root that we're looking for. All right, so now we just need to simplify these. This top one, we have 2 pi times 0 is just 0. So pi over 3 divided by 3 is pi over 9. So this one will be the cube root of 5 times cosine pi over 9 plus I sine pi over 9. They're going to be the same. The angles are the same. The next one, we have pi over 3 plus 2 pi times 1. Well, 2 pi is 6 pi over 3. So that's 7 pi over 3 divided by 3, which will be cosine of 7 pi over 9 plus I sine 7 pi over 9. And we still have the cube root of 5. And the last one, we have 2 pi times 2, so that's 4 pi over 3 would be 12 pi, plus the extra pi is 13 pi over 3, which will give us 13 pi over 9 for our new angle. So the only thing that's really changing here is the angle. And those are our 3 distinct complex roots. If we cubed each of those things, we would get back to that 5 cosine pi over 3 plus I sine pi over 3. And so that's the process. So let's do another one. keep the formula here so that we can see it. And let's let z equal 1. And we're going to find, let's find the fourth roots this time. So we're going to find the fourth roots of 1. What to the fourth power equals 1? And you're probably saying, well, 1, obviously, any root of 1 is going to be 1. Right, that's 1. We need 3 more. Oh, negative 1. True, negative 1 to the fourth power is also 1. Where are the other 2? And so we're going to look at this, and we might see, so we need a complex number. 1 is a complex number. Z equals 1 plus 0, I. A is 1, B is 0, which means the radius is 1. Tangent theta is b over a, so 0 over 1. So the tangent of theta here is 0. Inverse tangent, what angle gives us a tangent of 0? 0. So we can write 1 as the complex number 1 times cosine 0 plus I sine 0. Seems a bit big and excessive for that, but that's what we have. So we're going to find 4 of these. So the first one, the fourth root of 1, because z is 1, will equal, the fourth root of 1 is just 1. Like this piece of it is just like what we'd get when we'd plug it into our calculator. Oh, and when z equals 1, these are called roots of unity. I've never heard that before until this book, but if it asks for roots of unity, that means z equals 1, and we're just finding whatever roots that they're looking for. So we have 1, and then cosine of 0 plus 2 pi times 0 over 4 plus I sine 0 plus 2 pi times 0 over 4. The second one, the fourth root of 1, is going to be 1 times cosine of 0 plus 2 pi times 1 over 4 plus I sine 0 plus 2 pi times 1 over 4. The third one, the fourth root of 1, will be 1 times cosine of 0 plus 2 pi times 2 over 4 plus I sine 0 plus 2 pi of 2 over 4. And the fourth one, because we need 4 distinct roots, fourth root of 1 will be 1 times cosine of 0 plus 2 pi times 3 over 4 plus I sine 0 plus 2 pi times 3 over 4. So let's change our angles. 2 pi times 0 is 0, plus 0 is 0, divided by 4 is 0. So this is 1 times, it's cosine of 0 plus I sine 0. Well, cosine of 0 is 1, sine of 0 is 0, so this equals 1. That's one of them. And we expected that one. So next one, the 1 times that can change. So cosine of 2 pi times 1 is 2 pi divided by 4. This will be cosine of 2 pi over 4 is pi over 2 plus I sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so this gives us 1i. Oh, I to the fourth power is also 1. Interesting. The third power is a little bit more interesting because you get like 1 plus root something I. It's crazy. This one, 2 pi times 2 is 4 pi. So divide by 4 is pi. So this would be cosine pi plus I sine pi. So cosine pi is -1. And then sine pi is 0. So we have -1. And then we have cosine of 6 pi over 4 is going to be 3 pi over 2 plus I sine 3 pi over 2. And that gives us 0 plus I times -1, which is -I. So these are the 4 fourth roots of 1. And yeah, so now once we remember I, it's like, oh, that makes sense. Find the cube roots. It's even better because you don't just get I. You will get 1, and then you get 2 completely different things. So that's finding the roots. It comes from de Moivre's theorem, which was finding powers, which comes from the multiplication, which all comes from writing these complex numbers as polar coordinates from vectors, and it just kind of tying the whole chapter together and throwing in complex numbers because why not? So this is kind of what we're doing. There's a bunch of little topics here, but none of them are particularly difficult. This is probably the most difficult, and it's not mathematically difficult. There's just a lot of stuff going on. So make sure you take your time. Notice when I was writing it, it was a very slow process because I didn't want to miss anything. Be careful with that. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.